Yeah, next factor we are going to consider is carrier gas. In chromatography, in GC, carrier gas is also very important. Okay? And helium is the most commonly used carrier gas. But not only helium, but also other gases like hydrogen and nitrogen are also used. They give the same plate height, almost same plate height. Let's look at this Van Diemt plot here, okay? And at the this one, let's look at this minimum, and then at the minimum, the plate height is about zero point 0.3 millimeters. Okay, nitrogen gives a little bit smaller plate height. It is a little bit better than helium and hydrogen, but the difference is not very big. Okay, so they have more or less the same plate height. Okay, uh, but to reach the smallest, the plate height, the linear velocity, okay, is quite different. For nitrogen, the linear velocity is around maybe 12 centimeter per second. Okay, this is the flow rate. And for helium, it is about let me see, 23 or 24 centimeter per second, and for hydrogen it's faster, 35 centimeter per second. Okay, so optimal flow rate is in the order, in an increasing order, nitrogen, helium, and hydrogen. So using this hydrogen, we expect to have the fastest separation. Okay, because the flow rate can be increased a lot. Okay, so carrier gas affects the separation quite a bit. Okay, and this is illustration of separation uh, of let me see two this compound using different carrier gas. Okay, uh, with nitrogen carrier. Yeah, so the flow rate is 10 centimeter per second. Resolution is 0.87. Okay, resolution is bad actually here. Then these two compound is not well separated. Okay, well helium, with the helium carrier gas, you can increase the flow rate to 32 centimeter per second. Okay, and then this one, retention time decreases. Okay, and also R is increased to 1.44. This is okay, but this is smaller than 1.5, which is the normal satisfactory resolution. Okay, but with the hydrogen gas, carrier gas, you can increase even to 60 centimeter per second, and this retention time decreases. Okay, and also it increases resolution to 1.78. This is quite good, separation. Okay, this separation was done with wall coated open tubular column. When change the gases to hydrogen, resolution increases and analysis time decreases. This is better. Oh, hydrogen is must be the better, best carrier gas. But actually, it is not. Why? What are drawbacks in using hydrogen gas? You see, hydrogen gas is a very very active gas. So it may explosive. Okay, and it undergoes a catalytic reaction, and also hydrogen gas may degrade the pump oil. Okay, so here are drawbacks. As I said, catalytic reactions with unsaturated compound with hydrogen on metal surface may take place. No use with mass spectrometer. It breaks down vacuum pump oil in detector. Okay. main reason hydrogen was not used more often in the past. It forms explosive mixture in air when hydrogen is greater than 4 volume percent. Okay, so usually in gas chromatography, hydrogen carrier gas is seldom used. Okay, hydrogen and helium give better resolution than nitrogen because they diffuse more rapidly between phases. Okay? The smaller mass transfer in Van Dient equation, okay? Yeah, this part is smaller for hydrogen and helium carrier gases. If thickness of stationary phase is small, less than 0.5 micrometers, mass transport is dominated by slow diffusion through mobile phase than through stationary phase. Okay, in this case, so this mass transport, uh, this part, mobile phase is much. Uh, this one is slower, yeah, Mm, slow diffusion through mobile phase. Okay, this is dominated for a given column. With the radius r and the solute for k prime. This is a capacity factor. Only variable affecting the rate of mass transfer in mobile phase is diffusion coefficient of the solute through mobile phase. So diffusion coefficient in this order: hydrogen, helium, and nitrogen. For most analysis, carrier gas velocity, which is 1.5 to 2 times of optimum velocity at the minimum of a Van Dimter curve. Okay, here from this Van Dimter curve, yeah, maybe this is the minimum value here, but actually you increase 1.5 times or 2 times of this velocity. Okay, gas flow through narrow column may be too low for best detector performance. Okay, optimal gas for separation is used in column and the best gas for detector. Yeah? The called makeup gas is added between column and detector. Okay. Yeah, here is the guard column and retention gap. Guard column and retention gap is typically a 3 to 10 meter length of empty column in front of capillary column. Yeah? Purpose of guard column is to accumulate non-volatile substances. Okay, so non-volatile substances may affect the separation. So these non-volatile substances may be collected in guard column, okay, to protect contamination of uh, capillary chromatography and degradation of performance. Retention gap is to improve peak shape under certain condition. When introduction of large volume of sample by splitless or on column injection, yeah, for the this split less or on column injection, yeah, you'll see soon. Microdroplets of liquid solvent can persist inside column for the first few meters. Okay? Solute in the droplets are carried along with them and give rise to a series of ragged bands. Okay? So in order to avoid that, you use retention gap. Retention gap allows the solvent to evaporate prior to entering the column. Okay? And and also sample injection is very important. Okay, this is a syringe. Usually samples are injected through using this a syringe. Yeah, this is a sharp needle, and then you uh, insert this syringe into the injection port. Okay, and let's take a look at this uh, injection syringe. Okay, and uh, this volume is quite small, 1 microliter, okay, or 10 microliters. Okay. This is made of glass, okay, and this is a sharp needle made of, I think, the stainless steel. And here is the the graduation indicates the volume. And here is this is the what the piston. Okay, now ordinary injection, you may think that, yeah, this is for the taking sample and injecting it into the uh, injection port. And you may think that now this is syringe, and you insert this needle into the your analyte solution and take the analyte into this cylinder. Okay, it's okay, but it may not not give you a reproducible result. Okay, so instead, you first now you push this piston all the way down to the bottom of this cylinder, and then now you in air you draw back this the piston a little bit by this distance, and then that means that you inhale, yeah, you introduce air. Okay, and then now you put this needle into the solvent, and then you draw again by this amount, and then this amount of solvent is introduced into this syringe, and then again now you remove the syringe, and then you now throw the piston back, and then you introduce air again, and then you put this needle in your sample and draw this amount of sample. Okay, and then again you remove the syringe, and then you uh, draw this piston back, and then you introduce this air again. Okay, why do it this way? Okay, why do it this way? If there were a sample in the needle, the most volatile component would begin to evaporate and would be depleted before the sample is injected. Okay, let's assume that without this, okay, air purple region, and now this part is also filled with the sample, and also this part, yeah, this needle part, may be filled with your sample, and then when you insert this needle into the injection port, and injection port is quite uh, temperature is quite high, and the most volatile components in your sample may evaporate first. Okay, not at the same time. Okay, right? So the most volatile components would begin to evaporate and would be depleted before sample is injected. Okay, so even you push this needle to inject your sample, already in this part, some of your the sample already evaporated. Okay, that is not what you want. Okay? The air bubble behind the sample plug prevents sample and solvent from mixing. Okay, that's why you put this air bubble region. And also, what about this another air the region? Okay, this separates the sample and solvent. Okay, now this air now prevent these two solutions from mixing. Okay, the solvent plug washes uh, the sample out of the needle. Now you inject this sample first, and then air, and then if you push to the this bottom of the syringe, and then you also inject this solvent. Okay, and then solvent now washes the sample out of the needle. Okay, this one now takes maybe remained sample inside the syringe. Okay, um, and finally this air. Okay, air is now push all these solvents, yeah, into the injection port. Okay, this is called sandwich injection. Okay, sandwich. Yeah, this one. This sample is sandwiched between two air region. Also, solvent is sandwiched between the two air regions. Okay, many auto samplers are capable of this sandwich injection. Okay, this is a technique, but very important technique. Okay. Okay, now consider split injection. Split means to divide, yeah, into two. Okay, why do we need a split injection? Because if uh, you sample too much, yeah, if you now take too much sample here, but actually your chromatograph doesn't need that much sample, and then you have to inject small amount of sample into the column. Okay, that for that purpose, split injection is needed. Okay, look at this rather complicated configuration here. Yeah, so if analytes of interest constitutes more than 0.1% of the sample, split injection is preferred. Okay, how is it done? Okay, here you inject. Okay, look at this pale blue. This part is what? Hmm? This your sample. Okay, now sample is injected here. This is the injection port. Okay, but here this is column. Okay, uh, only small amount of your sample is injected uh, into the column, right? Why? Now this part is filled with your sample. Okay, but look at that. uh, and then here most of your sample now goes to other part. Okay, and only small amount of your sample now goes into this chromatographic column. Okay, here in this part your sample is split. Okay, so that is called split injection. A split injection uh, you know now allows only small portion of your sample to go into the chromatographic column. Okay, so split injection delivers only 0.2 to 2% of the sample to the column. Okay, most of your samples now doesn't go to the chromatographic column, but is collected. Hmm? Yeah, it takes other pass and then collected here. Okay, and then carrier gas is introduced from here through molecular sieve, hydrocarbon trap, and oxygen scrubber to remove oxygen, and then here. Okay, now it now carries this sample here, and but just a small part of the sample is injected into the column, right? And changing, and then this one. Uh, by controlling this flow controller, and then this one carrier gas may go to this part. Okay, to now take this not injected sample down to the vent. Okay, so injection temperature is kept high. This part is kept high, for example, to 350 degrees C. Oh, very high temperature to promote fast vaporization. Okay, where complete vaporization and good mixing occur. Oh, okay. I'm sorry. The brisk flow of carrier gas. This brisk flow of carrier gas now sweeps a sample through the mixing chamber. Yeah. Okay. This is here is a this is mixing chamber where complete vaporization here. Complete vaporization is done and good mixing occurs. At the split point, this is the split point here. Okay. A small fraction of a vapor enters the uh, the column, chromatographic column, but most phases through the needle valve to a waste vent. Okay, here. So most of your sample now goes to the vent. Okay. Split ratio ranges from 50 to 1 to 600 to 1. Okay, so most of the sample uh, will be vented. Okay. Inaccurate for quantitative analysis. The split ratio is not reproducible. But here, this split ratio is determined by this in this area, but this split ratio is not constant. Okay, so quantitative analysis may not be good with this injection. Okay, another injection type is splitless injection. Okay, splitless means what? There's no split. Okay, this is appropriate for trace analysis of analytes that are less than 0.01% of the sample. Okay, if you have a very small percentage of your analyte, okay, and then a split injection may cause too much low sample. Okay, so in the for the trace analysis, splitless injection is necessary. The glass liner is a straight. This is glass liner, but this is a curved one. But in a splitless injection, this is split injection. The glass liner is straight. Okay, there is no this part. Empty tube with no mixing chamber. This is mixing chamber, but here is no mixing chamber. Large volume, about 2 microliter. Yeah, this is quite a large volume for the split for chromatography. Uh, a large volume of diluted solution in a low boiling solvent is injected slowly into the liner with the split vent closed. Okay, yeah, here you close this split vent. Okay, and there is no mixing chamber here. Okay, injection temperature for splitless injection is lower than the split injection. Okay, then for the split injection, this temperature is maintained at a low temperature than in a split injection. Okay, this is appropriate for trace analysis. Okay, yeah. And there is another type of injection, which is on column injection. The on column injection is the direct injection into the column, without this kind of injection port. All right.